Want to welcome you all. Thank you all for coming and logging on today. This is MIT Innotherm, the International Colloquia on Thermal Innovations, co-chaired by myself and Professor Gong Chen at MIT, along with co-organizers John Leanhard and Evelyn Wong. This is our 14th colloquium. We've been doing a bi-weekly series. This one is on concentrating solar power. One of the first speakers we'll hear from is Fred Morse. He's a former senior advisor at Abengoa Solar. Fred has been involved in CSP since the 70s. He's managed the CSP and RD program under Presidents Carter and Reagan, and has also helped to develop and deploy about $4 billion worth of CSP projects. He'll give a brief 15-minute overview and high-level perspective on CSP first. Then we're going to go around a panel and have each of our CSP experts today talk about the two main questions that we've asked for the future of CSP. First, we're going to hear from Mark Mijos, who's from the United States National Renewable Energy Lab. He's the CSP group manager there, and he's been there for 30 plus years. Then we'll hear from Julian Blanco, who's the Associate Director of Plataforma Solar de Almeria in Spain. Then we were supposed to have Professor Zifeng Wang. One of his associates, Feng Li, will be filling in for him in his absence, and he is the Solar and Thermal PV System Laboratory Leader at the Chinese Academy of Sciences. Then we will have Dr. Avi Schultz, who's the U.S. Department of Energy Program Manager for CSP. And then we will hear from Cliff Ho, who's a senior scientist at Sandia National Labs and one of the pioneers of the approach to CSP using solid particles. One more time, the agenda for today, we're going to start with a 15-minute presentation from Fred Morse, followed by about an hour of discussion about these two main questions. And we'll wrap up. Please, as we're going, feel free to put your thoughts and questions in the Q&A. Use the Q&A button. You can give us questions that you have for the panelists, and also submit any suggestions that you have for how to improve this webinar. After we finish the discussion, if we've got time, we'll try to take some questions from the audience, and we may even also do some polling of the audience. This is being recorded. Colloquium will be posted on YouTube later. It's good to put your questions in because it may include questions that we did not get a chance to answer in the colloquium itself. We may be able to answer via the comment section on YouTube. If you prefer your question to be anonymous, please state so in your question. Just a reminder, this is an ongoing colloquium series. So there are upcoming events, upcoming colloquia. The next one on moisture control and heating, ventilation, and air conditioning. And on November 10th, membrane distillation for desalination. So I'll be your moderator today. After one last thing, when we wrap up, please put your suggestions of additional topics that we should cover on this colloquium series. And you're also highly encouraged to please sign up on our email list so you'll always get emails and updates and reminders about upcoming colloquia. So with that, I will pass it to Fred so he can give his initial talk. Oh, you're muted, Fred.
Okay, I've unmuted, and now I need to get back to my first slide.
All right.
Or move my slides. I don't want to move at all. I'm going to stop sharing and go back and start it again. I don't know what happened. maybe I go here. Okay, I think this will do it. Okay, I'm going to attempt to set the stage for the answering of the two questions that were posed. And what I'm going to do is I'm going to give you a quick overview of CSP, how it works, where it is, what we've learned from the performance of the 100 or so plants that are operating today. Talk a little bit about the emerging needs, which represent a market opportunity, which the questions really relate to, and then summarize that with the capabilities of CSP with thermal energy storage. So, as you know, to make electricity, you boil water, you make steam, you run it through a steam turbine, and you get electricity. Well, you can use the sun to make steam. I'm going to talk about two variations of that. There are others, but I'll just talk about two today. The picture you see in front of you is a power tower in Morocco. And the little cartoon picture shows you that the heliostats, the mirrors, track the sun, focusing the rays at the top of the tower where there's a receiver. There's a fluid in there that gets hot, goes down to the bottom, and it's either stored in tanks for use later or it is used to generate electricity at that time. The other variation is a parabolic trough. This is a picture of a plant outside of Phoenix, Arizona. A curved parabolic mirror focuses the rays of the sun on a tube, and once again, the fluid in that tube gets hot. It either then goes to make steam and generate electricity at that moment, or it's stored for later use. Now, these little schematics, or just the collector or the aerial view of a field, hides a lot of the rest of the plant. So the next slide shows you the trough plant and a power tower plant. And it shows you the solar field, the receiver, and the rest of the equipment that you need, the hot and cold tank, the heat exchanger, the turbine, the condenser, etc. And there are about 6.5 gigawatts of CSP. 80% of that are parabolic troughs, and the other 20% are power towers. And let me get to where they're located. You can look at the map and you can see if your country is there, and if it's there, you're very lucky because you too can have CSP in your system. But I'd like you to focus on the color bar at the bottom. It shows you the kilowatt hours per square meter arriving at that location in a year or in a day. Generally, for CSP, you want to be in the yellow, if possible in the orange, much better in the red, and wonderful in the purple. So Australia, the Atacama Desert of Chile, the Mojave Desert, for example, are excellent locations. Now, I mentioned that there are about 6 gigawatts worldwide. Keep in mind, those of you who know something about gigawatts worldwide, that PV is probably a bit more than that, and wind a bit more, and we'll hear one of the slides will show you exactly how much at the starting point CSP is. In the last 10 years, there's been activity up and down. A good year, over a gigawatt is built, and a poor year, about 100 megawatts. The point is, from this slide, that it started out in the US, then Spain came on, building about 2 gigawatts. Then the US added another gigawatt and a half or so. But now you see South Africa, Morocco, the Middle East, China, Chile, Israel, all building CSP plants. Now, let's take a closer look at this global market. First of all, look at the photograph. That shows you the other equipment in addition to the solar field, the tanks, the heat exchangers, the pipes, the condensers, the cooling units, etc. So there are 99 plants operating globally. Most of them are trough, 83 of them, 16 tower, the other technology, 1 linear Fresnel system operating. Of the 99 plants, a little less than half have thermal energy storage, and of those, most of those are molten salt. The storage is between 1 to 17.5 hours. It could be more if it made economic sense. There are about 3 gigawatts of capacity with molten salt storage and 25 gigawatt hours of energy storage. I should have looked up what the gigawatt hours of battery storage is, but I didn't. I have a feeling it's not as large as that. The cost is, for a large thermal energy storage system, about $80 a kilowatt hour, and the round trip efficiency is very good, very high. I'll go to my next slide. Now, the picture is of a 17 megawatt molten salt tower in Spain. It's been operating for, I don't know, around a decade. I want you to focus on the 3 lines in the graph. If you look at the green, that's the solar energy, and to no surprise, it comes on in the daytime and it goes off at night. And on a cloudy day, it has little jiggles and dips, and on a nice day, it doesn't. The blue line is the energy into storage. The storage is loaded in the daytime with the solar heat from the sun and discharged at night to operate the steam turbine. And the output of the plant in red is a solid straight line. Some little ripples, but pretty much operating at its design output. So this gives you an idea of the value of thermal energy storage. Now, this is, I like this slide, but I also dislike it. It's got too much on it. It's got hours of storage and type of CSP plant and capacity, but it's showing you that over the last 8 or 9 years, the levelized cost of energy of CSP is decreasing. It's gone down about 40 or 50%, and the lowest bid price was a little over 8 cents a kilowatt hour in Dubai for a large hybrid plant. And I believe, or IRENA, the source of this, predicts continued significant cost reduction over time. But keep in mind, CSP is at the very top of the learning curve. A study was done funded by the Department of Energy. If you look at the band of logos, the solar energy CEDO office is there. Gave a contract to NREL, which subcontracted to Solar Dynamics, and with the help of the other organizations that you see there, we took a look at the issues confronted by today's trough and tower plants. And in general, and of course we found a lot of issues in that study. In general, the trough plants operate very well. Some problems and challenges with heat exchangers for the storage system. Tower plants had some challenges in scaling up the hot tank, storage tank, and also some heat exchanger challenges. But the good news is that most of those problems have been solved. The overwhelming majority have been, and even better, people have learned how to avoid them. And this has been documented in a lessons learned report, which I think will allow future plants to be constructed with minimal issues. Terry Peterson, a colleague of mine, took a look at the fleet of 50 or 49 Spanish plants. Blue are the plants without molten salt storage, or without energy storage. There are 24 of those plants. And orange are the plants with molten salt storage. There are 15 of them now. Take a look at the orange bar. That shows the annual capacity factor. It's been drifting upward except for 2018, when they had extensive fires which blocked the sun to a noticeable amount. But you see, the plants are operating reliably. Same is true of the plants without salt. And the data suggests about a 96% availability, suggesting that these plants are very reliable. Now, I want to leave Spain and come to the US. In February of this year, right before COVID would make a conference like this impossible, we gathered the grid operators and utilities of the Southwest. They were represented by their CEOs or vice presidents or senior vice presidents. 8 utilities from 4 Southwest states, the CEO of the grid of California, of Texas, and the Western Coordinating Council. And we asked them, so if your state has a target of 100% carbon-free electricity generation, is that going to be a piece of cake? Will that be easy to accomplish? And they listed their needs, their evolving needs. For the utilities, reliability, 24 hours a day was the highest priority, and meeting the grid attributes, providing them 24 hours a day, was essential. They needed flexibility to meet the changing demand curve. They needed dispatchability, that is, they wanted the energy when they needed it and not when they didn't need it. They prefer diversity so that they can have some generation options. Fast ramping is essential, and capacity needs were now becoming more important than just energy. The grid operators expressed their needs. They needed to keep the system stable and balanced at all times. They too were concerned with fast ramping capabilities, and the last two are two sides of the same coin: resource adequacy or contingency reserves. Now, there was a third group in that conference. Compliments of the World Bank, who paid their travel. We had about 20 owners and operators of the leading CSP plants in the world. And they presented what those plants could do and what they cost. And the summary of the capabilities of CSP plants with molten salt storage is the following. Storage is long duration, 17.5 hours current maximum, could be more if it made economic sense. And many plants have run 24 hours a day for many days. So there's no problem with 24/7 operation. The plants can be hybridized in many ways, with PV, with natural gas or biogas, and a plant in Dubai and a plant in Morocco are doing just that, and we can get into that if it comes up. They're synchronous generation plants, so they offer a wide range of grid services. They're flexible in design and in output, and I'll illustrate that in a minute. They're dispatchable. You can have the energy when you want it, not when you don't want it. They're dependable. The 9 CEGS plants in the US ran for 30+ years with excellent output, and the Spanish fleet, as I pointed out, is running quite well. Costs continue to decrease, still high on the learning curve, but they're coming down, and you'll hear from the Gen 3 program of DOE, their ways of getting it significantly lower. And we have the best practices to guide new plants. I put an asterisk near hybrid and an asterisk near flexible. My last 2 slides are these. You can design the plant, you can vary the size of the solar field, the size of the storage, and really the size of the turbine relative to each other. So you can design it as a peaker, you can design it as an intermediate, or load following, or as a base load plant. And within that flexibility of design, you have flexibility of operation, the number of hours and when. So CSP with storage is highly flexible, which is a lot of the CEO said is the missing key to the realm. My last slide is this one. There was a study done by NREL and others where they looked at, I think, 28 locations around the Southwest over 18 years. and they looked at the 8 hours of peak demand, 365 days of the year. And they found that a CSP plant with 12 hours of storage could meet almost 100% of that peak demand. With 2% to 5%, I think I push this button and it pops up, there it is. Whoops, I went the wrong way. With 2 to 5% of natural gas, of what a natural gas plant would require for the same performance, a CSP plant with 12 hours of storage with a burner to burn a little bit of natural gas could meet 100% of that peak demand, 365 days of a normal year. So with that, hopefully I've given you a sense of what CSP can do, where it's headed, and I think I will stop at this point.
Thanks so much, Fred. That was a excellent talk. Thank you so much. I want to invite all the panelists to please go ahead and turn your video and audio back on. You can stay muted until it's your opportunity to speak. First, we want to go through the first of two questions that follow from Fred's presentation, which is really about whether or not CSP will play a major role in the future energy mix in terms of the global electricity production. Will its contribution be on the order of less than 1%, 1% or 10%? And why? And what's your argument why? So, Mark, are you available? Let me see. Yep. Great.
My screen isn't available because or my video isn't because I think you've stopped that.
Oh, I see. Let me see if I can turn that on.
So can you see my screen, by the way?
Yes, go ahead.
Okay. Yeah, so in a couple of minutes, I'll try to respond to that question. It's relevant because DOE, the Solar Office, is funding a future study, a solar future study. And so I grabbed a couple of slides that talk specifically about the market, mostly in the US, under a renewable solar futures. So Fred really talked about this. This is just another screenshot from the CSP Solar International Project Database. I don't really need to talk about that, but if you look at the top of this slide, you'll see that you can go to the NREL site to CSP and then go to Solar Paces. It's a nice database. You can look individually at the 100 plus plants that are either in operation, under construction, or even under development. And as Fred alluded to, where you're seeing the international markets was an initial market in the USA and in Spain, not particularly growing there, although we hope that will happen. I'll talk about that. But a lot of activity in the Middle East and North Africa, a lot of activity in China, we'll hear about that. Some activity in South Africa, and we hope activity in Chile, where the solar resource is extremely high. If I'm going to look directly at the US, NREL has what's called the Annual Technology Baseline, which is a projection of costs and performance of all the renewable technologies and conventional technologies. And then with that Annual Technology Baseline, you can go to a standard scenario viewer where you can look at the penetration of any one of those technologies, all those technologies together in this viewer. So I took a couple of screenshots. And the question is, will CSP in a future be less than 1%, greater than 1%, maybe 20%? And the answer is it depends, and we'll hear a lot about that. It depends on, in my mind, CSP hitting some very aggressive targets, but achievable targets of, let's say, Sunshot, which is 5 cents per kilowatt hour. If we do that, we can achieve greater than 1%, let's say 5% in the US. But what's interesting, this shows the US generation, assuming that CSP hits the 5 cent target, but assuming all the other technologies hit their aggressive but modest targets, then we see a lot of penetration throughout the US. But if you look specifically at the Western Interconnect and you look at how CSP, low-cost CSP, compares against PV in its mid-trajectory, we achieve high penetrations in the WEC regions, penetrations that are approaching 20%, and penetrations that are equivalent in generation terms to PV, utility scale PV, and rooftop PV. So the answer is yes, high penetrations regionally in a decarbonized scenario with low cost PV or CSP.
Thanks, Mark. Let's move on to Julian. Julian, you want to give your perspective?
Yeah, me also to based on one slide just to provide my opinion that I think that certainly the CSP will have a relevant role and contributing into the future. And I'm going to base this on two main arguments. One is the cost, and this is one of the main, let's say, critics or problem that is attributed to CSP, that it is very expensive. But if we put in a right perspective the question of the cost, we could see that it is still plenty of room to improve. This is, for instance, the evolution of the PV along the years since the 1990, when they started, let's say, the real, let's say, utility development scale. Here, this is indicated the average cost of the PV projects around the world, collected by international data from the International Energy Agency and IRENA, International Renewable Energy Agency. As you can see from the beginning, we have a very quick cost reduction, quick not in time, but representing against the global deployment of the technology. We have today, last year, about 627 gigawatts installed, and around the year 2007, we found some inflection point in which this very quick cost reduction start to, let's say, decline, but we have a continuous decreasing against the installed production. If we see the evolution of wind is replicated, it's basically the same. Here, story started early in 1980, and around 20 years later, 1998, we can find the same inflection point, and we have very similar total deployment worldwide, was about 650 gigawatts. And also we see that the profile is very similar. What's happening with CSP? With CSP, we are still into the, let's say, strike down curve. Yes. Certainly the story of deployment started many years ago in 1986, but today, if we consider the commercial running plant plus the advanced construction, we can see that we have around 6.2 gigawatts worldwide installed. And you can see we are not even reached this inflection point. So my question is why CSP is not going to behave a similar way? So there is still plenty of room to cost reduction on this. And the second argument to me is the policy, which is also a very important argument in all this story. Because when we have a system, we know from the physics, with a very large inertia, it's very difficult to change, to move. And in the case of the energy, clearly that we are active pushing policy to change the behavior that we have during the last century of based on fossil fuels and emission of CO2 and other gases. This is really very difficult to change. But I think that today everybody agree and assume that there is a very clear, let's say, movement. There is a complete assumption that our society will change, will arrive the practical total decarbonization within this century. Maybe some countries, some regions will take more years than others. But I think that this is, nobody doubts that it is no return point on that. And in this context, I have to remind that CSP with storage is one of the key elements for this, for a decarbonization of the system. It's like the keystone of the existing technologies, because based on the thermal storage, the dispatchability and the whole sustainability of the system simply is not feasible to achieve in some countries. I mean, today, without a significant contribution of the CSP, this decarbonization cannot be even imagined. So this is because we need also significant development of storage technology, energy storage. This is one of the important needed element from the future. But in all this picture, I think that clearly the future of CSP will be relevant, and the role in all this story will be more than one. I don't know, but even higher than 10%. I think that for sure. This is
Thank you, Julian. This is actually a fascinating slide. Every time I look at it, I feel like I learn a little bit more. It's really interesting to see the CSP time scale so much longer. I mean, I always thought about this plot, and I always thought that
we normally tend to see the things in a very short time.
Yeah.
When we put the right scale, maybe we change the idea that we probably have.
It's surprising that they all fit on the same curve, or appear to fit on the same curve, where the axis is gigawatts rather than number of installations. I always thought it needed to be like non-dimensionalized in terms of the number of installations. So anyway, let's go to Feng Li, who will be speaking on behalf of Zifeng Wang.
Okay.
Hello. I'm online now also.
Okay,
great.
So Zifeng, you will present by yourself, right? So I will stop the sharing.
I can, hello? Can you hear me?
Yes, we can hear you fine.
It's just my turn, Dr. Wang. So you want to present it by yourself, or you want me to speak on behalf of you?
I can present by myself.
Okay, no problem.
Okay.
Zifeng, are you going to present? Are you going to show the slides, or do you want Feng Li to share the slides?
Dr. Wang, would you like me to share the slides so you can talk?
Yeah, I'm working now for the Zoom, but have not success to share my screen. Wait a moment. Maybe you share screen, I can speak.
Yes, I think that's the way. Okay.
Thank you. I'm in airplane now. Just landing.
So can you see now?
Second page.
Yes.
After that, yes. In the first question, as a Q1, what is the CSP, the energy max? The total national energy consumed in 2019 was 4.886 billion tons of coal, TCE, of which non-fossil energy consumed accounted for 15%. In the map, you can see now is our green energy in 2019 and 2030 and 50. In 2050, our clean energy is 15%. This means output, not installed capacity as output as consumed in our national planning. But most of the green energy in this area in northwest of China, Qinghai, Xinjiang, Gansu, and in the Mongolia. But the energy load, most energy load in east and south of China. So we have transfer that kind of energy from northwest to east and south. most of renewable energy is PV, because PV is much cheaper now and cheaper in yearly and yearly. I think maybe 20, 15 years, the price, we cannot imagine the price, maybe 0.01 cents, maybe kilowatt-hour. But in the nighttime, nothing output from PV. So I think as in the major role in the future energy in China is PV plus CSP. During the night, CSP can output energy for the to the grid, HVDC. Last PVT.
Now
Last
only
one.
the first question.
Not that. First question.
We'll come back on
Not
the second
that.
question. We'll come back
Before.
on the second
We'll
question.
need to have
Back.
this
Next one. Yes, yeah. Not another. Okay. So as my opinion, in the future, in 2015, the PV, CSP plus PV, that's in the future, the max energy system, because our requirement and the distance. So very clearly, that's okay. It's my presentation about question 1.
Thank you, Zifeng.
Thank you.
Let's move on to Avi from DOE.
Yeah, let me just share my screen. So Mark already talked a little bit about some of the analysis that we've supported at DOE to answer this question, but I'd want to clarify a couple points and then talk actually a little bit about the barriers that we see to wider scale deployment of CSP. So we currently baseline the cost of CSP in the US with 14 hours of storage at about 10 cents per kilowatt hour. Those costs are dependent on a lot of US specific factors, including of course labor rates and commodity prices in the US. There are data points elsewhere in the world of lower costs for CSP. But we estimate that, as Mark mentioned, we need to get to about 5 cents per kilowatt hour to see wider deployment. And by wider deployment, what we see in some previous iterations of modeling that NREL has performed is potentially up to about 10 to 15% of US generation as being able to be provided by CSP. However, that is extremely sensitive to the kinds of scenarios that you envision for the US electricity market, particularly what you assume for other dispatchable, flexible energy resources, and whether you assume what you assume for cost and availability for technologies like, of course, batteries or natural gas plants. And of course, state level policies restricting the use of fossil fuels may, of course, impact the availability of those technologies. What you see here on the waterfall chart on the bottom left side of the screen is one potential pathway towards getting from where we currently are in cost today to that 5 cent target. And what I've circled in red is what we see as really almost 40% of the technology innovation that we need has to do with the power block, decreasing the capital cost and increasing the efficiency of the power cycle. And what we've seen in our modeling is that those are really, really big levers we have to reduce the levelized cost of electricity. And that's the reason why one real emphasis of our program, of our funding program at DOE, is developing supercritical carbon dioxide power cycles. So being able to use a much more compact, more efficient power cycle that instead of using steam as a working fluid uses supercritical carbon dioxide, has all of these benefits listed here in the blue box that we think are really, really key to increasing the deployment of CSP. Of course, many of these benefits are applicable to other thermal technologies as well, and we're working closely with our colleagues in the offices of nuclear energy and fossil energy on this effort. There are also, of course, a number of challenges to doing to commercializing this technology. And I won't spend too much detail here, just to emphasize that there are a number of ongoing research projects that we're working on, kind of summarized in the red box here, to improve the efficiency and really make this a realistic, dependable, commercialized technology. The final piece that I want to mention, of course, is that we're noting here that the high efficiency, 50% thermal to electric efficiency, is achieved at temperatures of above 700 degrees C turbine inlet temperature. And that means that we need to develop a thermal transport system, a CSP thermal transport system, that's able to deliver heat to that high temperature, high efficiency cycle. And that's what has already been alluded to, I think, by a couple speakers, is what we call Gen 3 CSP. So moving past Gen 1, the parabolic troughs that were shown, Gen 2, the molten nitrate-based molten salt power towers, moving to a thermal transport system that can exceed the temperature limit of molten nitrate salts, which is about 600 degrees C, and get to that 700 degrees C target. And we have, the way we've formatted this program is we have 3 competing teams led by Sandia, working on a solid particle-based system, NREL leading an effort on advanced molten salts, primarily molten chlorides, and Brayton Energy leading what we call a gas system, but is really actually using a supercritical carbon dioxide in the receiver loop, as well as in the power cycle loop of the Gen 3 system. And we're actually getting very close, just a few months away from these 3 teams actually submitting to DOE their fully integrated system designs for a megawatt scale test facility that we're planning to award up to $25 million to actually construct this integrated system in what's shown here in phase 3 of this competitive program, and actually validate that this fully integrated system can operate and deliver heat at the required temperature with thermal energy storage reliably. And we're expecting to do that early in calendar year 2021. So we're looking forward to making that announcement soon. I'll stop there.
Thank you, Avi. Let's also get comments from Cliff.
Hello. Well, hello, everyone. My name is Cliff Ho. I work at Sandia National Laboratories. I'm a staff scientist there. And with regard to the question, will CSP play a role in the future energy mix? I believe it will. And I think there are 2 primary reasons. The first is that there is an enormous need for heat. If we take a look at this chart from the International Energy Agency, about 1/3 of our total energy consumption is being used by industry. And of that amount, about 3/4, 74%, is needed for heat. And currently, about 90% of that heat is being provided by fossil fuels. So as we move away from fossil fuels, there's a huge opportunity from using renewables. Now, of course, concentrating solar power can provide that heat directly to provide that enormous amount of heat that's necessary. And if you look at that 74% of heat that's used by industry, nearly half is actually high temperature heat, above 400 degrees C. So concentrating solar power can certainly play a role in providing that high temperature heat that's needed in enormous amounts by industry. The second reason, oh, by the way, the heat demand is expected to increase by nearly 2% annually through 2030. The second reason I believe CSP will play a role in the future is that it can be economical. If you take a look at this plot here of the cost of energy per megawatt hour, this is in euros, but close to US dollars per megawatt. This is comparing different technologies, PV plus battery energy storage systems, CSP plus thermal energy storage, and PV plus thermal energy storage. And the takeaways from this study that was done by Schoeniger et al. Recently reported in Solar PACES is that if you look at the photovoltaics plus battery energy storage system, definitely the most economical for short duration storage, less than 2 to 3 hours. That's the gray regions here. colored by gray, where the top line is current costs, and then the lower line will be future projected costs. If you look at photovoltaics plus thermal energy storage, which is the red line, the band of red lines here, in nearly all cases, it's more expensive than concentrating solar power plus thermal energy storage, which is shown in the blue lines. And it can be cheaper than PV plus battery energy storage when you look at longer duration needs, with current costs greater than a few hours, or if you're looking at future costs, we're talking about greater than 4 to 10 hours. Now, similar conclusions have also been made by other studies as well. So the takeaway here is really that concentrating solar power plus thermal energy can play a large role when we're talking about the need for large capacity, long duration storage. Ase?
Yeah, thanks, Cliff. Lastly, why don't we see if Fred, do you want to add something on this point? You're on mute. Fred, you're on mute.
Right. I'm unmuted. I want to share my screen. Cliff, do you have to unshare? Okay.
Just did, yep.
Good. Now I'm going to share my screen, and I will get to this. Okay. So my answer is, your question, will it play a major role in the future mix and why? Will it play a role in the Southwest US? Yes. And any country on that map with good DNI and similar grid needs? Yes. How major? Well, you heard from Cliff and Mark the results of some studies. I'm just going to give you my guess based on the nighttime load, because night happens. And if you want to decarbonize the grid, you've got to meet the nighttime load. California has at least 20 gigawatts nighttime load. And I believe that CSP with storage can meet a significant percent of that load. I think a study needs to be made, but my guess is a quarter to half of that, if not more, which would be 5 to 10 gigawatts. That compares to the 35 additional gigawatts of PV that the state needs to meet its carbon reduction target. And why? Well, the reason is that CSP with thermal storage matches those grid needs that I showed you on the other slides. The flexibility, the dispatchability, the ramp rate comes on fast, it stays on. Some utilities said 4 hours won't hack it. We need more. And so I believe that the reason why it'll play a major role, and it'll play that role in compatibly with PV. PV will operate in the daytime. A CSP plant with storage will come on for the evening ramp, maybe sharing that with battery storage, but operate all night and continue through the morning peak. So I think the answer to your first question is yes. And I'll give you your screen back.
Great. So thank you all for that perspective. All of you seem to be great advocates of CSP. As we go into this second question, I'm going to kind of try to stir the pot a bit. And this question is really like, in what form will CSP survive? We heard a bit from Avi and Cliff about alternative embodiments outside of just using molten nitrate salts. You know, in all of you making your arguments around to what extent CSP is going to be around, what form do you think it's going to look like? Do you think it'll be molten nitrate, salt power towers? Will it be falling particles? Will it be something else? This is somewhat of a question around, you know, where would you place your bet? But one of the things that stood out to me, at least in looking at all the slides, which I wonder, it's also part of my own question, because I saw in the Q&A someone asked about, does CSP have to utilize DNI? And I think the answer to that is yeah, like that's the appropriate map you're looking at for whether or not the solar resource is appropriate. But then the question is like, you know, when you convolve that with the, as Zifeng showed, like when you convolve that with where people are located, where people are living, right? You end up having to transport the energy over a significant distance. And so I wonder if you now add the cost of transportation of the energy over that larger distance when you have to pull it from wherever maybe the DNI is highest, does it not make sense? Does that actually shift maybe the data Cliff was showing in terms of PV plus thermal energy storage? And also, if you're doing joule heating from PV or wind, are there other ways of doing thermal energy storage that might be even cheaper, that make that approach more viable? So that's my own personal interest is in joule heating from renewables and doing thermal energy storage. I think thermal energy storage on its own is undoubtedly likely going to play a significant role going forward. The question is really how is it going to play out and whether or not the solar field is going to be central. I mean, even in Avi's slides when he showed the cost reduction argument, the biggest bar ended up still being for the solar field, right? So one of the questions is really, do we need it, and what form do you all think will go forward and play the biggest role in the future energy mix? So why don't we go back around one more time on the panel, and Mark, do you want to share your screen or speak to that?
I'll speak and I'll share my screen, but there were a couple of questions. One was, does there need to be DNI? Yes, of course. The question was, does it need to be high DNI? And that's an interesting question, because our own future study that what Avi showed, and actually what this newer future study will show, is that, as opposed to getting into the 7+ kilowatt hours per meter squared per day, California type scenarios, Southwest scenarios, you can see CSP built in lower DNI. And lower DNI, we don't think of Texas necessarily as low DNI, but it is lower DNI. And we see a large penetration of CSP in that region under the Sunshot scenario, partly because there's a big load in Texas, but also partly because Texas can then export that from ERCOT to the Eastern Interconnect. So that's kind of an interesting result. More interesting, perhaps, is that we see CSP starting to show up in the Southeast, where the DNI is far lower, frankly, right? Is that believable? It's a model. You can always question the model. But what's interesting is that in the Southeast, you're actually limited in resources. I mean, it's low DNI for PV too. Biomass is there, but transportation costs, you've got wind resources and very good. So in a high decarbonization future, CSP actually shows up significantly in the long term in the Southeast. So that's interesting. I'll share my screen though, if you can see it, to the other point. I like what Cliff showed in terms of what are the other markets for CSP. He talked about process heat, and I think that is a good market for CSP. The other one that is not CSP, but is thermal storage, right? You talked about that. NREL has a couple of projects, not to focus on NREL, but whether we call it electricity thermal energy storage, pump thermal energy storage, Carnot batteries, they're all the same thing. There's a number of companies interested in taking grid electricity, creating thermal energy storage, either through resistance heating or through a heat pump, charging that thermal storage, and then dispatching that through some sort of a traditional or maybe not traditional power cycle. I think that's very interesting, especially when you start looking at long duration storage. Batteries get expensive at long durations, and eventually you need long duration storage. Let's say long duration is 8, 10, 12 hours or longer. Batteries are expensive, and our analysis at least shows that these Carnot battery systems actually become quite economical at those longer durations. And what's interesting, again, is that these are no longer limited to the Southwest, to high DNI. They can be established anywhere where there's a need. So I do like that pathway in addition to the CSP pathway.
Nice. Okay. Julian, you want to speak to this point?
Okay. Let me support again with another slide. Okay. So the second question to me is a very tricky one, because you are starting to saying if CSP survive. So I would like to answer with another question: why CSP is not going to survive? And here the main threat is supposing that the main risk for CSP is, you hint before, that if we achieve that PV is cheap enough, we can feed the thermal storage system, the molten salts, and provide the power dispatchability at lower cost than the existing current CSP plant. So we can remove all the rest and just to keep this. And the truth is that the current cost of the thermal energy that we can provide here in Spain, just with the existing technology and with our available radiation, the ENI is 2,100 kilowatt hour per square meter and years, is lower than $1 US dollar cents. So considering that there is still cost reduction potential, and that if we make a view of the alternative just in this scenario, that the PV electricity cost is average twice than that in location with higher solar radiation. And to this, we need to add the cost of the heaters in the range of 100 megawatt size, that technology that does not exist today, and plus the auxiliary electricity. So, I mean, it's not clear that we will we will arrive to this scenario in which just the PV will fully replace the CSP. So this is a game that still must be played, because there is plenty of room. And with regard to the challenge, which is the second part of the question, there is a huge number of topics that are today under research. And this is just, I mean, I reflect here a number of challenges like that are currently, as I said, many people working on. We have just a very few days an important international symposium, solar basis, and we can appreciate, we can see that this is, yes, we are close to achieve most of this target. I mean, to achieve new working fluids, either in towers or in parabolic troughs, to increase the nominal temperature, to increase the efficiency. We are targeting new receiver in towers, just to enhance the radiation that they accept, the temperature, the efficiency, much smarter heliostat, also to reduce the cost. Solar fields in parabolic trough, that I think that still there is at least 10 to 15 years of life, this technology, clearly. The development of innovative thermal storage system fluids in all the range of temperatures, I mean, in the 200 to 400 Celsius to many industrial applications, or even higher to towers or parabolic troughs. Turbines, there is one way that just to develop the supercritical steam turbine, just to improve the performance in 2-3 points, or just to the existing plants, and also the supercritical CO2 cycles that were connected before. And in addition to all this, the topic of the industrial process heat has been also commented before. This is a field in which there is not competition. I mean, solar energy here has not suitable alternative just to provide, let's say, this technology to a significant, large number of different industries and temperature range. So in my opinion, I mean, CSP will not only survive, but it will survive in a number of forms, just to provide not only power, electricity, but also heat. I mean, and all these challenges, I fully combined that will be achieved. There are nothing, let's say, extraordinary in just in achieve all this. And this is why, I mean, we are combined, that we are still in the straight line down of cost reduction that I commented, I showed you before, and still, I mean, I don't know if far or close to the inflection point, but there is plenty of room just to cost reduction and just to guarantee that the CSP for sure will survive.
Yeah, thank you, Julian. A very interesting perspective. Zifeng, you want to comment on this point? Feng Li?
Zhifeng Wang's computer is off
Okay.
power.
Okay.
You just speak for him again.
No problem.
Share the screen. For the second question, still some background on the why it will survive. Because in China, this slide is shared by the state grid, and the dark curve of grid equivalent load changes year by year. They have realized the problem with more and more PV and wind on the grid, and you can say if the output of new energy accounts for 60%, the frequency changes very much. So they say with the increase in the proportion of new energy output, after filling the frequency limit of the grid system increase and the security risk increase. In China, the grid security is of course, very important. So from this point of view, and they also shared if we have 4 gigawatt PV, and you can see the bus voltage, the changes, and then 4 gigawatt PV plus 1 gigawatt CSP, or with more CSP. And if we add CSP plants in the centralized access area of new energy, and the state grid problem will be solved, to some degree. And by 2015, and the solar, according to the prediction, the solar electricity generation, the percentage will be about 27%. And of that solar, the proportion, and we believe the CSP will account for at least half. Even though China has cut off the, we call it the no more tariff for that. But according to the ultra high voltage DC lines already built, there are several UHC DC lines in China, in the west of China, in the northwest of China, and to the east. But in fact, the utilization ratio is not very high because there's too much unstable PV or wind electricity, and we need the stable one. So the CSP plus PV, or even with wind, probably. And it's one way, and another is the peak shaving power source as a CSP. Of course, the cost is very important. And in the northwest of China, and the economic indicators is also the most important thing. And they also give Zhifeng Wang gave some the reference case in the DI of 20,100 and 1 megawatt solar tower with 12 hours of storage. And the capital cost is about 4,000, more than 4,000 US dollar per kilowatt hour, and about 1.05 US dollar per kilowatt hours. And of course, we needed to to cut off the cost is the most important thing. That's all. Thanks.
Thanks, Feng Li. Avi, you want to go?
Yeah, thanks. I'll share my screen in a second, but I want to maybe add one complexity to the question that we're answering in talking about, of course, the geographical difficulty of matching DNI to demand. We have to also, of course, consider the time constraints. We know, of course, that there are significant seasonal variations in solar radiation, of course, the diurnal variation. Plus, we've all been talking about, the value of PV and potentially CSP thermal energy storage technology surviving to be charged by PV. But of course, we know that there are often periods of time when we have, even during the summer, multi-day stretches of time that say even an 8-hour battery system is not going to be charged, by either PV or a CSP solar field. So what I want to show is, if I can, so I can show my screen. What are the advantages that CSP technology have to addressing those challenges? The advantages is, one, a CSP plant has a power block that can really be powered by any kind of thermal energy. Fred showed, I think at the end of his talk, that could be powered by something as simple as an auxiliary boiler. You could use a small amount of natural gas or even a renewably derived fuel to fill in those gaps in solar radiation. Or you can think about other, more complex indirect thermal energy storage systems. So you could even have a CSP plant have some kind of indirect thermochemical process where you generate a fuel on site that can be stored for very long periods of time stably to generate a fuel that could be, again, used on site or even transported off site, either to be used for electricity or to address industrial process heat. Of course, one of the challenges for industrial process heat, and it certainly is an interesting market, as Cliff showed previously, is of course matching industry to the DNI resource. So if we can use thermal energy to generate fuels that can be transported either geographically or in time, that's a strong advantage. I've also shown here on this slide just a schematic of what we've talked a little bit about as well, which is an electrothermal energy storage system. And as Mark kind of showed one iteration of that, this is kind of a more general schematic of a CSP plant that kind of operates more like a PV plus battery plant, where you can both generate or absorb electricity from the grid. And of course, using, one advantage of this is being able to use a heat pump to store electricity to get relatively high round trip efficiencies in the system. And of course, may increase the flexibility of a CSP plant. I want to spend just a little bit, another minute or two, just talking about thermochemical energy storage, because I think this is a really, as I said, I think this is a really interesting way to improve the flexibility or improve the utilization and applicability of CSP technologies. Because of course, we're not just consumers of thermal energy in the power cycle. We are also producers of thermal energy, and we have the advantage of being able to interface with a really, obviously long-lived thermochemical industry that of course exists in the chemical engineering field. And so we can think about using this thermal energy to generate fuels. And I'm just going to show a couple of examples of the kinds of projects that we're starting to think about in our program. I'm just going to give two examples of projects that we awarded in a recent funding opportunity last year, just showing the kinds of things we're looking at. We have a project with Arizona State that's actually doing a multi-timescale, designing a multi-timescale thermochemical energy storage system in which, to address the seasonal aspect, they are going to be generating hydrogen, which again can be either stored on site or exported into a pipeline system to be delivered to geographies regardless of DNI. Or on kind of the earlier TRL or technology readiness scale, we have a project at Michigan State which is actually trying to develop an entirely new kind of solid fuel based on metal oxides that can be stored indefinitely, generated inside a solar receiver, a solar reactor receiver, stored indefinitely, and again, transported off-site, essentially just like coal, to any either electric or industrial process consumer. So we think these are pretty interesting ways to think about the future of how solar thermal energy can contribute to the energy sector.
Very cool. Cliff, want to comment on this?
Yeah, I'd say that for the question of what will the future of CSP look like if it's to survive, to set the stage, there are three forms of energy that we really need, and they're all about equal. So we talked about heat, there's electricity, and then there's also transportation fuels. Okay, and that's sort of getting to what Avi was saying in terms of thermochemistry and how CSP can play a role. So heat, electricity, transportation fuels. And when producing these forms of energy, we also want storage. And in the past number of years, I've looked at various technologies. And one thing that I think a technology that's going to be able to address those needs is particle-based CSP and thermal storage. So this shows an example, just a cartoon of what that might look like, where rather than heating up molten salts, you're heating up particles that are falling through a receiver and getting directly irradiated by your irradiance coming from the heliostat field. And those particles, which can get heated to over 1,000 degrees, 800, even up to 1,000 degrees Celsius, you can store those hot particles before being passed through a heat exchanger to get the heat out of the particles, to power an advanced power cycle, as Avi mentioned, say supercritical carbon dioxide Brayton cycles. Cooled particles are then collected and then recirculated up to the top. So we've done testing as part of the Gen 3 program, and we've been able to get these particles well over 800 degrees Celsius. Now, in terms of the challenges with this technology, there are really two main challenges I'm going to highlight here. And those are basically getting the heat into the particles and then getting the heat back out of the particles. So this animation shows an illustration of the particles falling through the receiver, getting irradiated, getting to the high temperatures. But as you can see, there could be chances for particles to escape and heat to escape. So getting higher efficiencies, reducing those heat and particle losses is a big challenge. In addition, if you're talking about thermochemical processes where you're using these particles in a reactive sense, where you do a reduction or oxidation process to either generate hydrogen or synthetic fuels, you typically have to have a controlled environment. So typically a lower partial pressure of oxygen, and then there you might have to have some sort of windows or apertures. With regard to getting the heat out of the particles, we've been researching different heat exchangers. Here, this shows an example of just a shell and plate packed bed system, where you can imagine this being, picture an hourglass. Particles are slowly flowing past these plates. The hot particles then transfer the energy to the working fluid that's going through these plates. Again, that can be a high pressure supercritical CO2. It could be steam for your power cycle. Getting the heat out of the particles can be challenging. Surface area with these discrete particles is not as, say, high as a fluid. So some methods for increasing that particle side heat transfer coefficient include fluidization, for example. Despite these challenges, I still believe that particles are a good solution to all of these energy needs that I mentioned before. Again, there's heat and storing that heat for long duration, large capacity storage, producing electricity, producing fuels through either hydrogen or some sort of synthetic fuels, and or chemicals. Ammonia can be done through reactive particles as well. So I do believe that the future of CSP can include some form of these particle-based solutions. I'll say.
Great. Lastly, Fred, you got any comments you want to add on this?
I do. If I could, I'll share my screen for my last slide. Let me get to the next one. Okay. So will it survive? Yes. You've heard for electricity and thermal needs in areas of good solar radiation and in time with areas of even weaker solar radiation. What will it look like? Well, I think there'll be several embodiments. I think we'll see CSP with thermal energy storage as they are, just those two aspects for peaking intermediate baseload needs. More likely, I think we'll see these plants hybrid with PV, possibly with natural gas or biogas, because that would give a 24/7 operation at the lowest cost. I also think we'll see the Carnot battery idea, where we just have a big storage facility which gets its input energy from the sun through a CSP plant, or over generation from wind or PV, and it provides energy, electricity as needed. We'll see a lot of high temperature applications, as Cliff mentioned, for sure. And I think we'll see the strategic use of thermal energy storage for those weak solar days, a few cloudy days in a row. I believe there's a potential to use the molten salt storage for that need as well. I'd like to talk about non-technical challenges. People spoke about the technical challenges. I'd like to speak about the non-technical. Number one, there is a misunderstanding that CSP has to compete with PV on LCOE. It doesn't, and it never will. They're different. A bus doesn't compete with a truck, and a car doesn't compete with a bus. They're different. They're different capabilities, and they're compatible. We have to address the lack of awareness of what the current costs and capabilities of CSP with storage is. That's why we had that meeting in Sacramento. People need to know that the costs have come down as much as they have and the capabilities are what they are. We have to fix the misleading capacity expansion models that don't correctly use the current costs and performance. NREL's got that right, but there are a lot of capacity expansion models that get it wrong. And the utilities know how to buy apples, but now they need bananas. We have to modify the procurement, the RFPs, to go from cheapest to best fit for those needs that I documented on that slide. Cost matters. We have to continue cost reduction. The Gen 3 program that DOE is doing is extremely important to hit that goal, but so is the learning curve. Just build more plants. You could squeeze that supply chain. There's innovation. You can build plants faster, and that saves a lot of money. And last but not least, continue to improve the performance and the dependability of the fleet. So yes, it will survive, but it has those challenges.
Thanks, Fred. This is a really interesting discussion. Actually, Cliff, I just wanted to know, I really like the hot hourglass analogy. So I got a question. I guess I'm gonna kludge together several questions in the Q&A, and I want to get you all's varying opinions on this. Anyone can jump in wherever you like. But there's kind of this interesting question emerging as I'm listening to you all around how much does the future of CSP, which all of you seem to see as a bright future, there's going to be some role, how much of it hinges on these major cost reductions? Roughly, from obvious slides, it's roughly a factor of 2 or so from some forms of new technology that are not currently really deployed at scale, versus pushing down the learning curve, as Fred noted, right? There's these two components. And my question, and I think this is a bit reflected in the Q&A, is does the future of large penetration depend on only one or both, or is like an equal, like how important are these two respective modalities for cost reduction or penetration? Does anybody want to speak to that? Yeah, go ahead, Mark.
Jump in before the rest do. It does depend on both. And Craig Tershi, who I know, asked a related question, and that is, we've seen cost reductions for tower or for parabolic troughs by learning. Mm-hmm. And we've seen reliability improvements by learning. And if you look at the US, you had the first CEGS plants, cost reduction and reliability, it happened. Mm-hmm. If you look at Spain, cost reduction over time and reliability, it happened. The question is towers. What is needed there?
Yeah.
And how many? And I honestly believe in our best practices activity that one of the issues with CSP is going from market to market and relearning. That's difficult. But you don't need many new towers in any of those markets. Let's just say 5 to 10. You will learn and you will get cost reductions in that market. So look at China, look at Chile, maybe look at North Africa. I think it can happen there. And you can get a long ways towards cost reduction. And in those markets, the price may be fine. In the US, I think you need technology. The US is a tough market, very low natural gas prices. There, I believe you still need the technology improvements.
Makes sense. Makes sense. Anyone else want to comment on this?
Yeah, I agree with Mark. I don't think that they're mutually exclusive or independent of each other. Certainly the costs depend on the learning curve for both cost reduction and reliability.
Right, of course. Well, this goes, I guess, maybe also to Craig's question, which is, what is it that we need to learn with regards to increasing and the reliability on the towers? Where are the problems, and what is it that needs to be improved there?
I could answer.
Yeah, go ahead.
I could answer. In our best practices study, we looked at towers and troughs primarily or solely. In the towers, it's not the solar field. The solar field is basically reliable. We need cost reduction, but it's reliable. Where we need additional reliability is in two primary areas, maybe three. But it's the thermal storage, the hot tank. There has been some failures in the hot tank. They're engineering causes. They're very solvable. We just can't repeat the mistake. And then the other one would be in another traditional system, the steam to salt heat exchanger, the steam generator, molten salt to steam generator. It's a very known system, relatively known system, but ramping and part load operation is just not learned as well as it could have been, right? You just need more routine on those and understanding of that. Those are the two most concerning components in a tower plant, frankly.
Yeah, and I would say that in addition to those technological improvements for reliability, if we could do something to actually be able to scale down these towers so that they're economical at the 1 to 10 megawatt scale, that would be huge. So in terms of the power cycle that Avi mentioned, just being able to scale down these components, I think would be a huge advantage. Again,
Well, there
I'd
is
love to see
work.
1 to 10 megawatts.
There is work being done by an MIT alumni, Bruce Anderson, on a scaled down small tower with ceramics, and I mean, a very innovative. He is building a pilot test which should be running hopefully soon to prove that out. But that would fill a niche in the market, because sometimes you want to tuck your system in closer to the load, and it's unlikely you can do that with a 100 megawatt plus plant. So there is work being done on that concept.
This to me gets to an interesting question that about the plot Julian had on his first question around the learning curve. And what really jumped out at me when I saw it today was really the two arrows that show, okay, here's 2 points in time. And for PV and wind, it's much shorter. Like CSP, it's like 50 years and we're still on the very steep part of the curve, right? And so this gets to the real nature of like, what is driving that curve? Really, is it number of installations? Is it, what exactly is behind that? Because at the end of the day, I would argue, the time scale there may be so long, we're at the very early part of the curve, the steepest part, and that's actually 50 years already, and so the question becomes, is there a way to speed up the time scale of the rest of the tail of the plot?
The main reason to me is the number of installation. We are dealing just with 100 plants, commercial plants around the world on CSP. So this is certainly very few you compare with any other technology. Why there are so many plants so far? Because the effort of the interest so far has been very reduced, because people has not, let's say, visualized the relevance that this technology could have. Now we think that we are starting people are starting to have this kind of vision that this could be a relevant element of the mix, the technology mix into the future dealing with power. This is, and one of the drivers is that, from my point of view, is the necessity of dispatchability. So far, this has been no problem at all for two reasons, because we have plenty of fossil fuels, and we have still plenty of room for PV and wind, which are not dispatchable, to enter into the grid system. All the grids can handle 20, 30, even 40%, maybe depending on the percentage of the non-dispatchable without major problems. But going beyond that, I mean, you are facing significant problem that you need much smarter grids just to handle. And this is when, and this is why, this is the moment just that CSP could enter with a significant, let's say, visualization, a significant role. And we are just on the timing that we are progressing shortly, because the effort that has been devoted to both research and commercial projects on CSP has been very reduced. But we are on the moment that we can provide to the industry, let's say, a cost that could be achievable by the system just to introduce, and also to solve a problem when from the policy point of view, many countries, in Europe for sure, that it has been defined that the 100% decarbonization by 2050, this is the political, the final target. And for sure, when we make the assessment, the CSP naturally appear on the pool for the coming years.
I'd like to add something to that. In South Africa, they had several cycles of bidding. In like 4 or 5 cycles, the price came down 45%. If you build plants, and in Spain, by the way, they had a feed-in tariff with no competition, so you lost some of the benefit of the learning curve. I believe that if you have a market, and you have a market, as in Spain, is going to have 5 gigawatts, that will drive the price down. The whole supply chain that you build up, if you don't have another project, you lose it. If you have a supply chain and you constantly can get them to find ways to cut the cost, there is a lot. I think that the learning curve, the next 40% drop in price can come in a lot shorter than the first. And combine this learning curve combined with the work that DOE is doing to bring on the technical part, I believe will be there. Cost is critical, but we heard the utilities say best fit is more important than lowest cost. They need to meet the needs of the grid. If they don't do that, the cheapest is not going to matter.
Great points. Great points. Oscar, were you about to add something?
Yeah, if I could just add something. So I think Julian and Fred are saying something important about the policy implications. But if I could just kind of maybe say a word again about the technology, I think, you know, there's no question that the number of iterations of plants is important for the learning. And I want to emphasize that I think a big reason for that has been the technology limitations of steam cycles, which have CSP plants are obviously currently using, really give you a really high efficiency penalty for dropping below, let's say, you know, approximately 100 megawatts. And so that imposes a really high cost of capital burden, as well as just a high, you know, marketing burden to be able to raise the funds for a plant of that size. Finding applications that allow you to build much smaller step sizes in plant, I think, are really important from the technology point of view of developing the technology. And that may be supercritical carbon dioxide cycles, which, as I show, you know, potentially have the promise of being high efficiency at, you know, a much smaller scale. But of course, that's, you know, that's a technology that's under development. It's not commercial yet. But that's also why what Cliff showed about industrial process heat is important. You do have a number of process heat applications that, you know, certainly scale significantly less than 100 megawatts and may be appropriate for technology developers to focus on. Certainly the trough industry has benefited to that to some degree. Most industrial process heat applications out there are at temperature regimes that are most appropriate for trough or linear collectors. There are, however, applications that are probably more appropriate for towers. I mean, just to pick one somewhat at random, the cement industry is a large consumer of heat that requires temperatures, you know, in the range of 1,000 degrees Celsius or higher. You know, as I showed, there are potential applications for chemicals, for fuel synthesis, that again, admittedly is somewhat earlier stage, but I think it is important for us to consider those, let's say, smaller step size type projects that will allow developers to iterate on technology faster than they currently can with steam cycles.
Great points.
I would like just to
Yeah.
add just that the feed-in tariff was mentioned before, and I think it was a good point in the past in Spain just to make possible to push the industry just to develop, just to start the process. But it is clear that this is something that is not happen, will happen again. I mean, and this is what's also mentioned, that will be a critical point just to drive them to force the innovation and just to advance in the cost reduction. I mean, and for sure it will significantly help just to make possible that future plants will be different than the previous, just to develop, to continue this deployment and just to go in advancing in the cost reduction of the system.
Great. Yeah, thank you all for such a great discussion. It's been very, very interesting, and we're out of time for today, but definitely it's clear that this is a important and interesting topic to possibly revisit at some point. I just want to mention for those who have been able to stick around, remember we have future sessions coming up, one on moisture control and HVAC, one on membrane distillation for desalination. And please, if you can, make sure you sign up on inotherm.mit.edu, get on the email list if you are not already, to be reminded and get the links for upcoming sessions. Want to thank all the panelists for all your great insight and comments. This was a really good discussion. I learned a lot, and hope the audience did as well. Thank you all very much. I will stay online in case there are others who want to add things to the Q&A, but for now, we'll go ahead and end the session here. Thank you all very much.
Yeah.
Thank you, guys.